this will be our last topic for the semester, the Net Change Theorem. And the Net Change Theorem, it is an application of the fundamental theorem of calculus part 2, but it's more a reinterpretation of the fundamental theorem of calculus part 2 when the integrand measures a specific rate of change. And the rate of change we've seen most is velocity. So, well, example 2 and example 3 will involve velocity. But let's state the net change theorem. So you know, up here is the title of the topic, and here, this is just the statement of the net change theorem, so that's why net change theorem is written twice there. Theorem, net change theorem. When a quantity changes, the new value equals the initial value plus the integral of the rate of change of that quantity. So, the integral of the rate of change, for a given time interval tells you how the quantity is growing or diminishing during a certain time period. So the new value equals the initial value plus whatever the rate of change, or whatever the integral is measuring. Well, maybe I should say plus whatever is changing. And the integral measures that change. And with the notation of the fundamental theorem of calculus, A is the initial time, B is the end time. So a new value, f at the end time, equals the initial value, f at a beginning time, plus the integral on that time interval of the rate of change of that quantity. And remember, the derivative measures a rate of change. So let's look at 3 examples. The first one is more abstract, and the next 2 will be more, well, less abstract. Example, a honeybee population starts with 100 bees and increases at a rate of n prime of t bees per week. Great. What does 100, that says 100, not 106. What does 100 plus the integral from 0 to 15 of that rate of change represent? Well, by the net change theorem, this represents the initial value, and this represents the change from time 0 through time 15. Now, this integral is capturing everything that happens between time 0 and time 15. Time is measured in weeks here, so it's looking at what happens in these 15 weeks. It starts with 100, and this tells us what's happening during the 15 weeks, and what we're left with is the amount of bees in the population after 15 weeks. Maybe I should say the number of bees, not the amount. The number of bees in the population after 15 weeks. That says after. That doesn't really look at all like after. That does kind of say after. But this gives the number of bees after 15 weeks. Starts with 100, and then it changes at this rate, n prime of t. Let's look at this next example. A car moves due north. Now, there is some strange spacing in this example for a reason, which I'll explain. A car moves due north at 40 miles per hour between 2 and 4 p.m. Okay? The car moves due south at 50 miles per hour between 4 and 5 p.m. Okay? Find the net displacement and total distance traveled of the car from 2 to 5 p.m. So we're actually asked 2 things here. The net change theorem is going to give us one almost immediately, but the other one will be a little more complicated. Now first, what are these spacings for? Well, remember, velocity measures the rate of change of position. But velocity when you walk forward is different than velocity when you walk backwards. When you walk forward, velocity is positive. When you walk backwards, velocity is negative. Meaning, when a car is moving at a certain rate, we need to specify a positive versus a negative direction. Car moves due north. I'm going to call that the positive direction. Car moves due south. I'm going to call that the negative direction, which is a long word, so DIR works with that spacing. So, well, that's great. That tells us a couple things. It tells us which is the positive direction, which is the negative direction. Now, let's look at the statement of the net change theorem. When a quantity changes, the new value equals the initial value plus the integral of the rate of change of that quantity. When a quantity changes, the new value equals something. Right here, position is changing. The car is moving, so position is changing. The new position equals the initial position plus the integral of the rate of change of position. Velocity is the rate of change of position. But notice here, we have two different velocities. So in particular, our velocity function is defined piecewise. But with that, when a quantity changes, the new value equals the initial value plus something. So the new position equals the old position plus something. Meaning that the net change theorem is going to give us the net displacement. And then we'll discuss total distance traveled in a moment. Net displacement is the integral of our velocity function. Here we're going from time from 2 o'clock to 5 o'clock. So we'll say integral velocity from 2 to 5. What is the velocity? And I guess I'll write it down here. I already started. Well, the velocity is 40 at some time. $40 in the positive direction. When is that? From 2 to 4. What is the velocity from 4 to 5? It is not 50. Because the car is moving in the negative direction. The car is walking backwards, meaning the rate of change of position is negative. The car is walking. Yeah, I did just say the car is walking. So our velocity from 4 to 5 is negative 50. And now we have these integrals to compute. So we have 40t from 2 to 4 minus 50t from 4 to 5. And what does that equal? Well, 40t from 2 to 4 is 80. 50t from 4 to 5 is 50, and there's a negative on it. So the net displacement is 30. It's 30. What does this actually tell us? Well, our net displacement here is positive, which means that we're technically 30 miles north of the starting point. And if this came out to be a negative, then this negative would have taken over more, which means that the net displacement would have been behind where you started. But here, it's positive 30 miles. So I'm just going to say it like this. I never like how positives look in front of numbers. So I'm just going to leave it as 30, and I'm going to put in parentheses north of where we started. Now, a couple things on this. Well, why do these integrals work? Well, 40 times the 4 minus 2 is 40 times 2, which is 80. 50 times 5 minus 4, 50 times 1 is 50, and there's a negative, so that becomes negative 50. Now, there are a couple observations to make. The fact that this was 2 to 5, we could have said 0 to 3, and then 0 to 2, 2 to 3. You get the same number. Because you could zero out your time. But this, why does this look like the right-hand side of our net change theorem? Well, we can assume we're starting here at position 0. So that f of a in the net change theorem statement, you could, well, you don't have to write that it equals 0, but we'll assume we're starting at position 0. So we found the net displacement. Now let's find the total distance traveled. Well, before doing that, we could have figured out both of these without any calculus with this example. 50 or 40 miles per hour north for 2 hours, you go 80 north. 50 miles per hour between 4 and 5, you go 80 north, then 50 south. So from the starting point, up 80, down 50, you're left with 30. What would the total distance traveled then be? Well, it'd be 80 plus 50, 130. In the next example, the numbers won't work out quite so nicely. But how can we use an integral to find the total distance traveled? Well, the net displacement wanted us to treat walking backwards as a negative. It was 80 minus 50. That's what net displacement wanted to happen, and it did. The velocity when you walk backwards is negative. What does total distance traveled want? Well, total distance traveled wants positives to count positively and negatives to count positively. What can we do to make negatives count positively? I don't like how that looks. Well, we can integrate the absolute value of velocity. The absolute value of the positive velocity will still be positive. The absolute value of the negative would then be positive, meaning this walking backwards would count positively. Now, how do we integrate an absolute value function? Well, we'll see. I'm debating what I'm going to have to erase. This actually will take a good amount. Yeah, maybe it won't. Actually, it probably won't. The next one will, though. Well, first of all, our velocity changes for the first 2 hours versus the last 2 hours. It's 40 from 2 to 4, and it's negative 50 from 4 to 5. We still haven't taken an absolute value yet. Absolute value of 40 is 40. Absolute value of negative 50 is 50. And do this integral just like before. You get 40t from 2 to 4 plus 50t from 4 to 5. You get 80, in this case, plus 50, which equals 130 miles is the total distance traveled. Now, how do we integrate an absolute value function in general? Well, next example. So we did get the answers we expected just from reading the question and noticing 80 miles north, 50 miles south. Now, what does this look like, before going on to the next example, what does this look like graphically? Well, we can actually see all of these pieces graphically. If we graph the velocity. Observe this graph. Velocity. So this will have velocity. We'll also need the negatives. And the x-axis will have time. We're looking from 2 to 4. We had velocity of 40. From 4 to 5, we had velocity negative 50. that is a graph of this velocity function. And since these integrals measure areas, you could see that if you moved your 0 over to 2, it would give you the same positive and negative areas. So, what does the integral give? Well, as mentioned before, these areas. The integral of the velocity, the net displacement, gives you this area, which is a rectangle, so it's 40 times 2, area 80, and then it subtracts this area, 50 times 1, which is 50. So the net displacement treats this as a negative, and you got 80 minus 50. The total distance traveled says, no, I want this to be a positive. And it treated it as a positive. And you got 80 plus 50. Let's look at a more general example with a more complicated velocity function. Given the velocity function v of t equals 3t minus 5 feet per second, find the net displacement and total distance traveled from time 0 to time 3. Well, let's start with net displacement. And let's do it, I guess, up here. Well, net displacement, remember, is the integral of our velocity function. In this case, from time 0 to time 3. That's a 3 up there. And I guess I can just erase it. And then rewrite it. What's our velocity function? 3t minus 5. And we're going from 0 to 3. How do we integrate that? Well, power rule, 3/2 t squared minus 5t from 0 to 3. And what do we get? Well, at 3 we get 27/2. 9 times 3 gives you 27. Minus 15 gives you negative 3. Oh, minus 15. And notice here, at t equals 0, you do get minus 0 minus 0. So this just gives us negative 3/2 feet. So whatever this velocity function is measuring the position and the velocity of on time 0 to time 3, it goes back 1.5 feet. How about the total distance traveled? Well, traveled, 1L in American English, canceled, 1L in American English. So I use 1L. Well, I'm going to have to erase this net displacement because this is probably going to take all 3 of these boards, maybe even more. Maybe not, I don't know. We'll see. But remember, the total distance traveled wants those negatives to contribute. So we take the absolute value of velocity. Equals what? Well, we have 3t minus 5 as our velocity function. So we want the integral of the absolute value of 3t minus 5 on 0 to 3. Well, how do we do that? Our velocity function, where do I want to write this? Will that fit here? Yeah, I think it'll fit here. Yeah, that should fit on that third board. How do we integrate this? Well, the absolute value treats positives and negatives differently. So if we have a curve that happens to look, say, something like this, the absolute value is going to break at that x value. And if that x value happens to happen between 0 and 3, then it's going to split. If it doesn't, well, computation is much simpler. So we need to find this x value. Well, this is a line, so we do know it's going to look like this, y-intercept, positive slope. But what happens at that x value? Well, the y value is 0. So what we need to do to find that x value is set 3t minus 5 equal to 0. Add 5, divide by 3 3t minus 5 equals 0 when t equals 5/3. Let t equal 5/3 there, the 3's cancel, you get 5 minus 5. So we know from that this integral is going to split at 5/3. We know the integral is going to split at 5/3. We still haven't taken the absolute value. How do we deal with the absolute value? Well, now we've broken our curve into what's above the x-axis and what's below the x-axis. Now, this one is a line. Which line is it? Well, it's the line I erased. It's this line, y-intercept -5, x-intercept 5/3. This one is a line. Since we can graph that line conveniently, we know which piece is below the x-axis and which piece is above. Because remember, the absolute value isn't going to do anything to the positive piece. It will flip the negative piece around. So here, what do we get? Let's write it like this. That looks bad. Well, actually, just the integral sign looked bad. We get this. Why? Well, first, notice the second piece is the same because the absolute value of this positive piece of the curve is itself. The absolute value of positives is itself. Are themselves, I guess I should say. The absolute value of a positive is itself. What about for this negative piece from 0 to 5/3? This piece below the x-axis. Well, the absolute value of a negative is the negative. The absolute value of -5 is -5. The absolute value of negative all this is negative all this. So -3t, -5, gives you -3t plus 5. And we can now compute these two integrals using the power rule, fundamental theorem calculus part 2. And fundamental theorem calculus part 2. Yeah, I guess I'll just keep going across the bottom. This might fit. No, I don't want to. I'd rather write higher. So I'm going to continue this computation up here. Continue that up there. And what do we get? Well, we have -3/2 t squared plus 5t from 0 to 5/3 plus 3/2 t squared minus 5t from 5/3 to 3. Now we just be careful in our substitution and simplification. What was I about to say? There are some integral properties you could use to simplify it a little and make some observations. I'm just going to go through this. 5/3 gives you 25/9 when you square. Plus 5 times 5/3, 25/3. Substitute 0, you get 0 over 0. That's convenient. Plus what? Well, there's no convenience over here. 3 squared, 27. 3 squared 9, 9 times 3, 27, divided by 2, minus 15. And then we want to subtract what we get when we substitute 5/3. 3 halves times 25 ninths minus 25 thirds. You could have also, in doing the absolute value, left it the same and flipped those bounds around with the definite interval property. Now, one of the potential shortcuts you could have gotten to is, these look similar. They don't cancel, but they are the same values. So let's add all these together. Well, what does this turn into? Negative 25 over 6. Why? Well, 3 and 9 cancel a 3. That turns into a 3, so you have a 3 and a 2 down there, which makes a 6 and a negative 25. Plus, I'm going to leave 25 thirds alone. Plus, well, 27 halves minus 15 is negative 3 halves, so I'm just going to combine them now. Minus, well, there's that 25 sixths again. And plus 25 thirds. Negative, negative, 25 thirds. And what do we get when we add all these together? Well, I'm going to combine thirds, then sixths, then leave the halves alone. 25 and 25 thirds make 50 thirds. 25 thirds plus 25 thirds. Negative 25 sixths minus 25 sixths gives us what? Negative 50 sixths. Negative, if you have negative $25 and you spend another $25, you're left with negative $50. Replace the word dollars with sixths. And then the halves, we still have negative 3 of those. What does this equal? Well, 50 thirds minus 50 sixths. Well, 50 sixths reduces to 25 thirds. 50 of something minus 25 of something gives you 25 of those things. Minus 3 halves still is there. Now combine these. What do you get? You get 50 minus 9 over 6, the cross multiplication thing. 50 minus 9 all over 6 gives you 41 sixths feet. So during that time interval, the object moved 41 sixths total feet and wound up 1.5 feet behind where it started. So these computations are definitely among, it could be argued this is more difficult than the limit computation for the area under a curve. Could be argued that that is more difficult. This one is definitely easier to, make a slight counting error. But in it, in integrating an absolute value, we found where the absolute value crossed the where the curve crossed the x-axis, and then we interpreted the absolute value. What's below is negative, what's above is positive. And with this example, I used a graph for the interpretation, but you didn't have to. Another way you could have done it is by picking an x value in this interval. X value, to pick a t value. If t equals 1, what's inside here is negative. So that tells you on this interval, you're taking the absolute value of a negative, which tells you, to simplify it, which tells you the absolute value makes the inside a negative. And that would work for any value within these endpoints. For the other piece, you would do the same thing. For simplifying this one, take a t value in there, say t equals 2. 2 is larger than 1 2/3. Let t equal 2, you get 6 minus 5, which is 1. So you're taking the absolute value of a positive which is a positive. But the graph, you know, if you could do a graph on that, it would probably be a little less work. But do practice an example like this. And do keep the graphs in mind. They are helpful for problems like these.